Our project is on the classification of physical activity using EMG recordings. Our team is Team Datalogy, and our team consists of Bhavya Sharma and Elisa Ye. Our project focuses on using electromyography, which is the process of recording electrical signals from the skeletal muscles to monitor health and assess neuromuscular connection. And one specific application is kinesiology, or the study of principles of mechanics and anatomy in relation to human movement. Our dataset is comprised of 4 subjects, and each subject performed 10 normal activities and 10 aggressive activities. There are 8 electrodes on each subject, and continuous records of muscles for each activity, resulting in about 10,000 samples per activity with a sampling frequency of 200 Hz was obtained, and one data frame records activity for one action. Since there are 20 actions per subject and there are 4 subjects, we have a total of 80 data frames. EMG signals conducted from the surface of electrodes are typically noisy and complicated. So our goal is to build a successful classification model which will help biomedical engineers understand the time series features that differentiates activities. Applications of the model range from performance enhancement of an athlete to detection and diagnosis of anomalous behavior in muscles. Our hypothesis is to suggest that normal and aggressive actions vary in signal pattern amplitude and frequency, and hence the collected signals can be classified. Our goal is to build a classification model to classify an aggressive action against a normal action. We first compared rock signals of a normal activity to an aggressive one. And here we see the activity of handshaking versus punching. We then did some preliminary data processing involving filtering, rectifying, and smoothing the data. We created time series features from data using a sliding window approach. And we created 3 combinations of sliding windows. One for a window size of 500 and a step size of 50, one for a window size of 1000, a step size of 100, and one for a window size of 2000 and a step size of 200. Just a wave signal in raw or processed form does not convey much information, so it was necessary for us to extract features from the signals to feed into our classifiers. Thus, we calculated various features including absolute energy, entropy, Fourier transform coefficients, Euler transform coefficients, along with basic statistics like mean, variance, kurtosis, and skewness. To conduct the modeling, we stacked all actions of a subject and labeled them as 0 for normal and 1 as aggressive. We used 4-fold cross-validation approach, such that we trained on 3 subjects and tested on 1 subject on each fold. We performed preliminary classification on the 3 combinations using all features and assessed the results. The results for our preliminary classification is shown as follows. We see that for naive Bayes, logistic regression, and random forest, the accuracy rate is pretty high, but the best performance is still for a window size of 1000 and a step size of 100. So we proceeded to select this model for our classification task. In the ROC curves for all of the 3 combinations, we can see that combination 2 seems to have the best results. We proceeded to do some feature engineering by modifying our feature space. So we generated 6 additional feature spaces and varying them based on whether or not they include top features or whether or not uncertain features, unfit features, or low priority features were removed. And each feature space ended up having different number of column features, which we aim to reduce. Here shows the performance for each of the feature spaces in terms of accuracy and average accuracy, and we identified feature space 6 as our best space because of the high accuracy produced by our best model, random forest, and the fact that it has the least number of column features. Here are the results for our best classification model. And our RC curves for feature space 6 shows random forest to be the most optimal. On the right, we see the performance accuracy for all the models in all folds. And we see that random forest performs consistently well across all folds. Some of the top features we identified include quantiles, Fourier transform coefficient, absolute sum of changes, maximum, minimum, mean, median variance, aggregated linear trend, absolute energy, autocorrelation, and so on. And these were based on the feature importance generated by our best performing random forest model. We then did some basic visualization of some of the features for normal versus aggressive actions across all channels. And we can see that for some particular channels, such as right thigh, right ham, left thigh, left ham, the aggressive action values tend to be much higher. More details on our findings and methodology will be shown in our report. Thank you for watching.